Okay, ji, lecture number 30, I'm just repeating it. So lecture number 30 over here, these are the contents over there, and today we are talking about the synchronous motor, the phasor diagrams, the torque, and then if we have time, we are going to talk about this constant excitation part. In synchronous motor, you are going to give A, B, C three phases, which is going to produce a magnetic field with speed ns, of course, and that is going to be given as 120 F by P. And now in this machine, you are also going to give a DC supply over here at your rotor, and this time you are going to use slip rings also because you are going to provide DC. You can't use any brushless exciter or pilot exciter scheme because here the motion is going to be created by you. Otherwise, in the generator part, the motion was already inherently available because of the turbine used over there. So this is going to produce a north pole and south pole, and if there is a south pole here and north pole here, as this magnetic field rotates, which means the ns rotates, the rotor is also going to rotate with itself, and there is going to be a locking mechanism, and this is a very simple mechanism for synchronous motor. The good part of this machine is this, that you are not going to have any speed regulation is going to be equal to 0, or the slip is also going to be 0. So this is the only machine in AC family which is having 0 speed regulation, which means it has a very good use in the paper industry because the thickness of the paper when it is going to be made from cellulose is going to be dependent upon the speed with which you are going to run the machine. So thickness of the machine or thickness of the paper depends upon, or even if you are working on maybe cotton industry or maybe something thread industry or somewhere else, the speed is very critical. But in thread industry, synchronous motor is not that much used. The reason, it's very, very expensive. So this synchronous motor is only used in some packaging industry. I'm talking about the packages plant in Pakistan, Lahore. Over there, they use this synchronous motor because they have the state-of-the-art thing over there. Now, the worst part of this machine, which is in 5.3 article, is this, which I'm just going to ask you to go through it. It's not a part of your course, but just go through it for the understanding that this machine is not self-start. What is the problem over here? The problem over here is that this machine, if you provide AC to the stator, it starts to rotate at revolving magnetic field at 120 F by P. No issues. The rotor stands still with the north and south pole. So it has a lot of inertia and mass. And when you are applying 50 hertz, number of poles are supposedly 3000 RPM. It's a huge speed. So what happens? The stator starts to rotate with a very, very high speed, and the rotor, since it's at rest, it does not lock itself. It has a lot amount of inertia. So to start this machine, there is a set of rules or a set of ways which you can actually run this machine. The first way is you start this machine as a synchronous generator and then turn it into a synchronous motor. Okay? That's the most easiest way if you have a turbine with you. The second way, which is very, very beneficial also, but it's only applicable, is this, that you start rotating your rotor by hand or by some other mechanism. If you don't even have a turbine, maybe you have a motor over there, you start rotating it, and at the very same time you give A, B, C also a phase, then you can take out the apply. This way you can actually start running it. The third way, which is very, very important on this machine, is this, that you have supposedly a supply which can have a frequency from 10 to 30 hertz, give a reduced frequency, which means now ns will be a little slower, the rotor can follow it. These are three mechanisms. But the fourth one is the most expensive one and the most commonly used, which is actually that on this rotor, now see this very carefully what I am going to do over here, I am going to install on this shaft of this machine another type of winding, and this winding is going to be also placed on this south pole. And this winding, if you can see closely, it's actually a replica of an induction machine. So if you are going to get an induced EMF inside this winding because you are having a rotating magnetic field. So at one time you will be having something across, cross, dot, 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 dot. Okay? So what will happen? Induction phenomena will start to take place, and this machine will start as an induction machine because induction machine is a self-start machine. But as soon as this induction machine starts, you will open circuit this winding and the machine will now become a synchronous motor. This type of winding which I am talking about over here is called as amortisseur winding. It's a French word. I always use the I always miss the spellings of this machine, the winding. Let me copy the winding name. This is Amor. This is your, this is, come on. So I have, come on. What I have done? Okay, I have this one. Okay, Amor. This is your winding. This is a very specialized winding. It's actually an induction motor winding which we have placed on the North Pole and the South Pole, and certainly its connections are coming out because the slip rings are also there. So this means the two wires are actually coming out. First of all, you short them, and then the machine has started. So what will happen if your NS was supposedly equal to 3000 RPM, your NR would be, when you start it as an induction machine, will be approximately 2950 RPM. Well and good, no problem. As soon as it's done, open the winding terminals and now give supply DC to your rotor. So this time, and one thing very important, in this make and break situation, first of all, you are going to give DC supply and then break the amortisseur winding over there. So you are going to have the NR again now escalated to the same 3000 RPM over there. And now this is working as a synchronous motor. So this is the one big problem. And this type of winding, as you can see on the pole face, it's given this type of winding called as amortisseur winding. And this is very, very expensive and actually makes the synchronous motor again more expensive over there. So this is the reason you won't find a lot of machines having synchronous motor in our industry. It's available in the paper industry. The packages have it because of the very good reason that it has a percentage speed regulation or slip equal to 0. The equivalent circuit diagram is the very same, nothing special changing over there. The only thing that is changing, previously if you remember, if for the generator the current direction was opposite. This time now this is in the direction of the IA shown over there. So these are three phases, and you can connect these three phases in your Y configuration or delta configuration. One thing from your synchronous generator chapter, very important, if in the exam you are asked to draw the circuit diagram, and if it is not specifically mentioned that you have to draw the one phase or three phase, okay, go with the one phase. But if it is asked to you that you have to show the circuit diagram with delta connected or Y connected, then please show these three connected in Y or in delta with the rotor diagram also. This is the rotor diagram over here. So you have this one. And as anticipated, this is very important because the direction of current is changing. So this means this time your V phase is now going to be equal to IA plus plus IARA plus JIAXS. So this time it's not negative sign. So this time it is EA plus IARA. Second, just wait. Okay. Okay, yes, sorry बेटा, question. तीनों को कनेक्ट बड़ी सिंपल है इसमें. अब मैं सिंक्रोनस मोटर की बना रहा हूँ. अगर यहाँ पे इफ़ आई हैव अ वाई कनेक्टेड सिंक्रोनस मोटर, this is your resistance, this is your access over there, and you have this one, supposedly this is plus, negative, this is your Y connected, and another source shown over there, this is plus, negative, with again the synchronous reactance plus the leakage, the resistance, and then you have another, this one is wrong, and you have it. So you have it negative, positive, and you have this one. So this is your JXS, this is your RA, this is your EA, this is your EA, this is your EA, this is XS, this is RA, in fact JXS, not simply XS, and this is RA. This is Y connected. So this is rotor, bilkul exactly same like this. You just draw it with on the left part or the right part. Let us say, it's not going to be. Rotor and stator, they don't have any, they are only just providing the flux. It has no physical connection over there. So this is very important over here. So now, direction of current. Here, the direction of current is inward. If it was the other way around, supposedly, then this was going out. This is the synchronous generator, this is the synchronous motor equation over there. If this is changed to synchronous generator, this changes to V phase EA minus IA RA minus JIA XS. Please don't miss the vector forms on the top over here. So the only difference is the negative sign and the positive direction of current actually. So this means now, one thing very important, let's go to the case if there was a synchronous generator and that synchronous generator is going to be converted into a synchronous motor. So if I had a synchronous generator and assuming, now one thing very important over here, I am going to assume that IA, RA, they are very, very small. So I'm not going to draw them in the circuit phasor diagram. So if I had a synchronous generator and that synchronous generator was working supposedly in lagging load, which means this is my V phase, and I have my IARA, this is my IARA, and certainly when I will extend this one, so this one would be my not exactly true, I hope this is okay. So this is my JIAXS, agreed? Okay? Now the last part is this EA. Now this is your EA and this is your delta. Where is gone? Light gone? 99. Light आ गई है, इसको ऑन करो दोबारा. सिर्फ झटका खाया उसने. Just turn it on. Please listen. This is a synchronous generator again, and this is JIAXS, EA, and over there. And corresponding to this one, certainly this means that this vector and this vector, this one is EA sine of delta. So this means that now this generator is actually producing power and giving it to you. Now I want to convert this one into a motor. Okay? Listen this very carefully. In the book they have just given like 4 or 5 lines. You won't understand it. Please. So this EA sine of delta, if it is showing over here as this positive, so this means this is actually supplying power to some load. And now I am going to assume 2 things. One thing, I am going to convert this machine, which is actually a generator mode, into a motor. And how I am going to do it? I am assuming that this synchronous generator was connected to some turbine over here. And that turbine was being supplied from some hydel power or any other gas steam or whatever case over there. And this synchronous generator was connected from that V phase to your infinite bus bar, which means that V phase is not changing. So 2 things over there, that synchronous generator is connected with the turbine, it's connected with the infinite bus bar, V phase is not going to change. Now corresponding to this diagram over here, which is this diagram, if you see over here, in this diagram, you have to draw 3 magnetic fields which are actually taking place inside your machine. Now, what are those 3 magnetic fields? If you have gone to lecture number 2, the armature reaction lecture, you must have an idea on this one. V phase is actually the net voltage available as an output. EA is the induced EMF and IA is the current. And if you remember the lecture number 2 from their synchronous generator, V phase produces, I will just change the thickness over here. V phase produces B net, EA produces B G. Who has taken the lecture? Come on. किसी ने नहीं लिया lecture? आप दोनों ने तो लिया अभी खत्म हो जाएगा. This is BR because the rotor is actually providing that flux, so this is BR. And IA is going to produce BS because what is IA? IA is the current flowing inside the stator, so it's going to. So these 3, so what is B net over here? These all are vectors, please, so don't worry. So B net is equal to BS plus BR, and this is actually that armature reaction I was talking about in the very start. So V phase will produce, if I draw it over here, V phase will produce the same, and this will be, I will be calling it as B net. Now since B net is equal to BS plus BR, Now EA is going to actually produce this one. I'm just going to show it over here with the same angle, I hope. And this is going to be that BR over here. This is your BNet and BR. Now, since BS plus BR has to be equal to BNet, and we know what was IA, I will just copy this IA over here, and this is my, so this was my IA over here. Now corresponding to this IA, because if I have a wire flowing over there, I guess I've given this example in that lecture also. If I have a wire flowing over here, current is flowing over here, just take a DC example, the flux is produced around this wire. So magnetic field lines are flowing out of it. So it's 90 degrees to that current flowing inside that wire. So this means that my BS is going to be at this point and it's going to be at 90 degrees to IA. And if I copy this one has to be equal to this length. So this is your BS over there. ये थोड़ा सा angle इसका differ हो सकता है. I will change this one. In fact, I will copy this one from here. It's easy to actually copy this one over here, and this is your BS. So this is your BS over here. Got this? B net is equal to BS plus BR. This is your generator working. Now, if you want to convert this one into a motor, the first thing you are going to do, turbine is lost. Turbine ne power dena band kar diya. It's not giving the power. Grid se bhi wo connected hai. So what will happen? Now it will convert into a motor. But when it will be converting into a motor, what will happen to this phasor diagrams? That's the question over here. Now if you see over here, your torque is equal to, I'm just using the formula over here, which was equal to KBR into B net. Okay? This is a formula you must have encountered over there. I'm not going to proof of that one. KBR into B net. I have two over there. If you use your right hand rule to find out, you have two forces, R cross F. You use your right hand rule to find out the direction of torque. You use your BR to B net, the torque is inward. And all of these vectors over here, these BR, B net and BR, they all are moving in the anti-clockwise direction. Now what this means actually, it's a generator. Generator ko hum move kar rahe hain in the anti-clockwise direction. And it's a generator, it has a motor phenomena taking place inside it, which is trying to move it in the counterclockwise direction. So they both are actually trying to cancel each other, but in steady state it's rotating because it's working as a generator. It's the same thing. If you remember your DC machines, I told you एक motor के अंदर generator phenomena हो रहा है, इसी तरह से generator के अंदर एक motor phenomena हो रहा है. So it's the same thing happening over there. So you are applying some torque from your generator. Let me call it the turbine torque actually. Let me call it as the turbine torque. And that turbine torque is actually exceeding, or it's actually exceeding the T induced torque of your motor action taking place inside it. Now what has happened? The machine has lost this turbine torque. Now what will happen? This EA vector which is producing BR, इसकी speed slow होगी क्योंकि अब turbine को हम power नहीं दे रहे, power का flow कम हो गया या जो भी कुछ हुआ है, steam का flow कम है. So this BR will actually now come below this B net. And as soon as it comes below the B net over here, this angle delta which हम use करते हैं यहाँ पे KBR cross B net को KBR B net sine of delta कहते हैं. So that torque actually, now BR vector is below B net. ठीक है? What will happen? Now torque will be in the other direction. So the torque produced now, the motor phenomena will increase, and now if I draw this one from your book, they have the phasor diagram. I will just draw this one. So now this one is your again V phase. I will draw this V phase and I will draw in parallel. This is your B net over here. EA is now going to be over here. This is going to be your BR. So this means your EA is going to be over here. I'm just drawing both of them simultaneously. Agreed on this one, ji? Now to complete the phasor diagram, what was B net equal to BR plus BS? So this means my BS is going to be equal to this point. So this is my BS over here. All of these are vectors over here. And if this is BS, if I just copy this one, if this is my BS, I will take this one over here. and this is my BS over here, not exactly the exact diagram, but anyway, I'll just change it, don't worry. So if this is my BR, this is your BR. कोई मुझे बताएगा where is going to be IA now? ये पिछली डायग्राम, टेक द रेफरेंस फ्रॉम दिस डायग्राम. हमारे पास ये फेजर डायग्राम पहले से थी, IA की डायरेक्शन हमारे पास पहले से थी. वी टुक दिस IA 90 डिग्रीज टू दिस BS. दिस वॉज अवर BS. हमने इस BS को यहाँ उठाया. द मैग्नेटिक फील्ड डायग्राम वॉज कंप्लीट. नाउ वी आर टेलिंग यू दैट द रोटर इज नाउ लैगिंग बिहाइंड. पहले क्या था? द रोटर वॉज एक्चुअली गोइंग फॉरवर्ड देन द net magnetic field. This angle delta was positive. Now this angle delta, which I will mark over here, this angle delta has now become as a reference negative. Still angle आप जिस direction में measure करो. The current, if you extend this diagram now, this one if it is extended, it will be 90 degrees to this one. I will draw this one over here. So now I will just trying to make it 90 degrees. So not actually this one. So the IA is going to be this one. The current was previously lagging. Now it has become leading. And this angle has changed to from negative angle. So what has now changed? The machine is now, what is the generator mode? Now it has gone to the motor mode with these three vectors over here for, this is the magnetic field diagram and this is your phasor diagram over there. And one thing very important, whenever you are drawing these diagrams, even in your CP or whatever, please always extend these lines, maybe with a pencil or something, and then draw, because this looks still 90 degrees. I have not used any compass or something, but if you extend it, it's still better, because अगर आप अंदाजे से बनाओगे, they are not never going to be accurate. So this is a synchronous motor, and this one is a synchronous generator which is working over here. Now the interesting part over there, if you see, I will just take off this BS because ये BS इस diagram में नहीं आता. But what is happening over here? Your synchronous generator V phase was equal to EA plus IRA is ignored over here. So this was equal to JIAXS over there. Now if you complete this phasor diagram, I have to add JIAXS, and that diagram is going to be equal to, this is actually going to be not BR, this is going to be EA over here. Okay? So now when I have to actually add this vector, this is going to be in this direction. So this is going to be JIAXS. Now one thing very important, see this carefully. आपने V phase vector पहले बनाया, EA आपको नहीं पता होगा इनिशियली, बिकॉज योर V phase इज इक्वल टू EA प्लस IA. आप पहले करंट IA बनाएंगे, उसके बाद उसका नेगेटिव लेंगे, बिकॉज हेयर व्हेन यू आर गोइंग टू टेक इट, आपने इसका हेड जोड़ना उसके साथ है. वाई? बिकॉज योर EA इज इक्वल टू V phase माइनस JIAXS. So negative of that vector. अगर आप इसका IA का नेगेटिव बनाओगे, that is in this direction. This is that 90 degrees, this is that JIAXS over there. So आप इसको उल्टा रखोगे. So EA plus JIAXS and then you have V phase over there. So this is a diagram, phasor diagram for your synchronous motor. This is your magnetic field diagram when it is converted from a synchronous generator into a motor over there. Now this generator, when it is working, there are two conditions. I'm just going to do one over here, and I will give a recording maybe like 15-20 minutes for the next one. So if this generator is working at a constant excitation and plus load is changing. Now what this means? This means that the load is going to increase, but EA, which is equal to K phi omega, omega is a speed which will be constant because it's a synchronous motor, no speed change. Flux phi is dependent upon IF current, that is the field current, so excitation is also not going to change. So what is going to happen to this phasor diagram over here? Now, there are two cases. I can start my diagram from what type of load, it's totally up to me. Supposingly, I will go with the same diagram and I will just copy this diagram and maybe just little increase in the size, and I will show you that this is my diagram, not that much increase over here. Now, what is over here? In this diagram, this distance and this distance, this is proportional to P, agreed? Why? Because your P was equal to 3V phase EA sine of delta divided by XS. V phase कांस्टेंट है, ग्रिड से कनेक्टेड है, हम सप्लाई सेम है, EA भी कांस्टेंट है, EA साइन ऑफ डेल्टा चेंज हो रहा है. So now the one thing is excitation constant है. What this means that now this EA vector, if I can draw this in some, so this is my diagram actually. ये थोड़ा सा अभी भी मुझे तंग कर रही है. I will make this one here like this. So this EA can only move in a circle as shown over there. Now what happens? मेरे पास load बढ़ना है. What this means कि this distance of y-axis has to increase. So the only way around is it, if I want to increase it this, that I will change the orientation. Okay, I used to use the thick one. The next one is this one. So what has happened now? The power has now increased to this portion. Let me call it P1. So now this is P2. And certainly P2 is greater than P1. Now, drawing this vector, which is now EA, let me draw it EA. They both are magnitude same. The only thing that has changed is this delta. This was supposedly delta 1. Now this has changed to delta 2. Over there. Now, this diagram is still not complete because I have to complete this diagram. So I will have to make this diagram. Okay, come on. So, okay, this is completing itself. JIAXS dash. So this is JIAXS dash. Let me change this one. Now, corresponding to this vector, अब आपने IA इसका plot करना है. This is very important. So when I have to plot the IA, I have to extend this line again, as I told you. And when you have extended this line, now you are going to make it perpendicular to this line. And that perpendicular, supposedly, that comes out to be at this point, like this. And this time, the current magnitude has increased. Why increased? Because load has increased. So this means now this is IA dash, and this angle is again 90. Now, supposingly, this again has an increase more. अब मैं दोबारा इसको increase करता हूँ. My size is actually the diagram. नहीं ठहरो. हो गया होगा टाइम. आप खुद लेट आए हो ना लेट. वो असाइनमेंट कर रहे थे ना वो फिर. So let me complete it. Okay, now I am going to increase it furthermore. So now my diagram becomes like this. This is again EA, and corresponding to this over here, this one is my GG input power. This is a motor. This is a motor. This is a motor over here. So this is P3 over here. Now with this P3, if I have to draw this vector now, from this point to this point, I will just add these two, and come on, yeah, why this actually fills the color? Fill coloring has to be here. Stopped. Okay, so now this one is your J. Come on. This is your JIA double dash XS. Now, कोई मुझे बताएगा ये करंट लैगिंग आएगा या लीडिंग आएगा? If it was exactly 90 degrees to this one, it would be a unity power factor. The current IA would be like this, in phase with V phase. But here this is a little bit back. So what this means that now my current, if I draw this one on over here, I'm just going to draw it with some other color so that it's a little legible. So now this current, if it is going to be, this is going to be here, this is going to be 90, and this is IA triple dash. What has changed over there? Your power P1 was smaller, then P2 was smaller than P3. So you have your P1 to P2 and P3 over here. Agreed Ji on this one? Any questions on this one? So what is changing over there? Your excitation is constant, which means EA is equal to K5 omega is constant. Your power changed from P1 to P2 to P3. And whenever you are asked to draw this phasor diagram in exam, please draw at least, I have drawn 3 over here, at least 4 phasor diagrams embedded on it is one, which means 2 are leading, 1 on unity power factor, and the 4th one over here. You can draw the 4th one over here, which means I am asking about this diagram up till this point, and then this one over here as EA, and then your IA over there. And one thing very important, this IA and IA dash, so this means magnitude wise, if I write it down, IA dash is certainly larger than your IA magnitude, and then your IA double dash magnitude is also larger than your IA dash. So this will continue to go on. Load bada to current bada. But the power factor is also changing, and this is the power factor, and synchronous motor is the only motor in the family of AC machines which can give you a lagging power factor also and a leading power factor also. So this is a constant excitation with load changing over here. I will upload the second part on this one.